Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. We live in an age of data overload, where petabytes of information flow around us every second. Most of this data is presented visually, through screens and charts, or acoustically, through voice and sound waves. But what if the next great frontier in machine learning wasn't sight or sound, but smell? This is the domain of olfactory computation, the radical idea of encoding complex digital information into distinct, reproducible chemical signatures, allowing AI to perceive and analyze the world through the vapors of computation. To understand this, we first need to appreciate the profound sensitivity of scent. The human olfactory system is an analog masterpiece, capable of distinguishing trillions of different smells, reacting to chemical concentrations down to parts per trillion. Yet, for decades, computing struggled to digitize this sense. A photograph is easy to encode, pixels and color depth. A sound wave is straightforward, frequency and amplitude. But a smell? A smell is a dynamic, multidimensional mixture of volatile organic compounds, or VOCs, where the slightest change in chemical gradient completely alters perception. Traditional electronic noses, or e-noses, have been around for years, used primarily in quality control or security to detect simple, specific substances. Is this milk spoiled? Is this air toxic? However, these devices act more like chemical sensors than true noses. They generate a complex electrochemical response pattern, a fingerprint of the chemical environment. The breakthrough in olfactory computation involves flipping this challenge on its head. Instead of analyzing an existing smell, how do we intentionally create a smell that represents abstract digital data? Imagine a large data set, a climate model with thousands of variables, or a high-frequency trading platform tracking hundreds of stocks. Converting this numerical data into an olfactory signature, or a smell vector, requires a sophisticated translation layer. Researchers are developing algorithms that map data features onto specific chemical components. For instance, high volatility in the data might correlate with a high concentration of a sulfur compound, a sharp, negative smell, while stability might correlate with a specific terpene, a softer, earthy smell. The resulting scent is not designed to be pleasant, but to be mathematically meaningful and chemically stable. This is where machine learning becomes indispensable. The AI is trained to recognize patterns within these complex chemical gradients. Instead of processing a matrix of numbers, the system processes a synthesized chemical event. Why use smell? The immediate advantage lies in data compression and rapid classification. A complex data set that might require a massive visual rendering could be compressed into a single, rapidly distinguishable chemical cocktail. The AI learns to bypass the tedious feature extraction of traditional data analysis and instead performs rapid pattern recognition on the entire chemical signature. One of the most promising applications is in anomaly detection. When dealing with massive, real-time flows, such as monitoring a nuclear reactor or a critical infrastructure network, a sudden change in data variables, a data spike, can be instantly represented by a drastic, unexpected chemical gradient shift. The system doesn't just register an error code. It registers a smell that is far outside its trained parameters, enabling quicker responses than traditional dashboards. Furthermore, this technology is accelerating the field of synthetic olfaction. Just as we have digital printers for images, scientists are building digital scent printers, arrays of microvalves and chemical reservoirs that can rapidly mix and disperse precise, digitally defined scent vectors on demand. These aren't air fresheners, they are data output devices. In medical diagnostics, this approach is already showing early success. Training an e-nose system to identify the subtle VOC profiles associated with diseases like Parkinson's or certain cancers is essentially training it to recognize a specific disease smell vector. By abstracting this concept, we move toward encoding any complex relationship, from the health of a forest ecosystem to the stability of a stock market, into a chemically readable language. The vapors of computation aren't just a novelty. They represent a fundamental paradigm shift in how machines sense, classify, and communicate complex information, potentially adding a fourth dimension to our digital world. For more incredible facts like this, don't forget to subscribe and turn on notifications.